We concluded our last video with a theorem that said if yp is a particular solution of a non-homogeneous differential equation, then the general solution can be written in terms of y1 and y2, solutions of the associated homogeneous differential equation with non-zero Wronskian, as y equals y sub p plus c1y1 plus c2y2. And since we learned how to find the general solution to any homogeneous second-order differential equation with constant coefficients, we can solve any non-homogeneous second-order differential equation with constant coefficients of the form ay double prime plus by prime plus cy equals g of t, so long as we can find one particular solution, y sub p. We now need a technique to find one particular solution, y sub p of t, to the non-homogeneous differential equation. That particular solution yp will depend on the function g of t. Thus, our approach will use g of t to determine the form of y sub p. We'll look at several examples where we find y sub p for various functions g of t. In this first example, we will find a particular solution to y double prime minus y prime minus 6y equals e to the 2t. So we need to find a function y of t that is a solution to this differential equation. That is, we need a function y of t that balances both sides of the equation. Since e to the 2t appears on the right-hand side, we will need e to the 2t to be on the left-hand side in order for both sides to be equal. The easiest way to achieve this is to try the form y of t equals a e to the 2t for some constant a. To see if this y of t is a solution for some value a, we check y of t in the differential equation. To do this, we need to compute y prime of t, which is 2a e to the 2t, and y double prime of t, which is 4a e to the 2t. Now checking this in the differential equation, we get y double prime, which is 4a e to the 2t, minus y prime, which is 2a e to the 2t, minus 6y, which is a e to the 2t, all must be equal to e to the 2t. Simplifying the left-hand side yields the equation negative 4a e to the 2t is equal to e to the 2t. Thus, we can conclude that for a equals negative 1/4, y of t equal to a e to the 2t is a solution. That is, y of t equal to negative 1/4 e to the 2t is a particular solution to the differential equation. This method of finding a particular solution is called the method of undetermined coefficients. To continue this example, now let's find the general solution to y double prime minus y prime minus 6y equals e to the 2t. We saw that if y sub p is a particular solution to the non-homogeneous differential equation, then the general solution to the non-homogeneous differential equation can be written as y sub p of t plus c1y1 plus c2y2, where c1y1 plus c2y2 is the general solution of the associated homogeneous differential equation. And we just found the particular solution y sub p of t equals negative 1/4 e to the 2t. Thus, we can find the general solution to the non-homogeneous differential equation by finding the solution to the associated homogeneous differential equation. Y double prime minus y prime minus 6y equals 0. And we can get the general solution here by looking at the characteristic equation r squared minus r minus 6 equals 0. Solving this, we get our two roots r1 and r2 are negative 2 and 3. Thus, the general solution of the homogeneous differential equation is y sub h equals c1 e to the negative 2t plus c2 e to the 3t. Combining this with the particular solution of the non-homogeneous differential equation, we can finally build up the general solution of the non-homogeneous differential equation, which is y of t equals negative 1/4 e to the negative 2t our particular solution, plus c1 e to the negative 2t plus c2 e to the 3t, the general solution of the associated homogeneous differential equation.